Near the beginning of this prompt, the passkey is 28,884. Then come almost 1 million tokens of text. At the end, the model is asked, what was the passkey? With standard attention, each token is compared with every earlier token. For 1 million tokens, that requires about 500 billion comparisons in each attention head, in each layer. Qwen2.5-1 can process this prompt, even though its longest training sequences contained only 262,144 tokens, so how can it handle almost 4 times that length? The first step is to make the model use information across the full 262,000 tokens it does see during training. A long training sequence does not guarantee this. If the model is predicting the last word in "the cat sat on the," all the information it needs is nearby. Most next token predictions are like this, so examples that require distant text are rare. Qwen adds training tasks that cannot be solved from nearby text alone. The model must reconstruct a removed passage, find a paragraph near a distant keyword, or restore shuffled paragraphs to their original order. Training also increases the maximum sequence length in stages: 4,000, 32,000, 65,000, 131,000, and finally 262,000 tokens. On the 128K ruler benchmark, the score rises from 37.6 to 87.6 over this progression. The later training stages made the model much better at using distant information within its training range. But training still stops at 262,144 tokens. To process 1 million, the model must also handle positions that never appeared during training. Why are those unseen positions a problem? When attention compares 2 tokens, it uses both their contents and the number of positions between them. A model trained on 10 token sequences encountered distances from 0 through 9. It never encountered 10 or more. To avoid those new distance values, divide the longer input into chunks. In this example, the training length is 10, but the chunk size is 6. So, the first 3 chunks contain tokens 1 through 6, 7 through 12, and 13 through 18. Consider 4 token pairs. Inside the first chunk, token 5 attends to token 2. Their true distance is 3, so the positional calculation uses 3. Across the first boundary, token 7 attends to token 6. Their true distance is 1, so the positional calculation uses 1. Now let token 18 attend to every token in the first chunk. The actual distances to tokens 1 through 6 are 17, 16, 15, 14, 13, and 12. For the positional calculation, Qwen uses 9, 8, 7, 6, 5, and 4. Add a 4th chunk and repeat the comparison from token 24. The actual distances to tokens 1 through 6 are now 23, down to 18. But the positional calculation again uses 9 down to 4. So the method does not change every large distance to 9. For each non-adjacent chunk, it repeats the same sequence of trained distance labels. Nearby distances remain exact. The tokens being compared do not change, only the distance labels used in attention are remapped. Together, these 3 position rules are called dual chunk attention, or DCA. One more problem appears in a longer input. The attention weights for each token add up to 1, so they can become spread too evenly across many candidates. Qwen first multiplies the scores by about 1.3, making the strongest matches stand out more. This adjustment comes from a method called yarn. DCA remaps the distance labels and yarn makes the attention weights more focused. Neither reduces the number of comparisons. 1 million tokens still produce about 500 billion attention scores in each head and each layer. The next step is to avoid most of them. So which of those 500 billion attention scores can Qwen avoid calculating? Before Qwen generates its first output token, it processes the entire input and builds the KV cache. This stage is called Prefill. With a 1 million token input, attention can take more than 90% of the prefill time. Place the attention scores in a grid. Each row is a query token. Each column is a key token. Each cell is the score for 1 query key pair. Most scores are small. The large scores often concentrate in a few columns and diagonals. A strong column means many queries give a large score to the same key. A strong diagonal means each query gives a large score to a key the same number of positions behind it. Qwen calculates every score in the final 64 query rows. Because these tokens come at the end, those rows cover almost the entire input. Suppose many of these queries give a large score to key token 20. Qwen selects column 20. Suppose each query gives a large score to the token 3 positions before it. Qwen selects that diagonal. For every earlier query, it calculates only the scores in the selected columns and diagonals. It skips the remaining cells. This method is called MInference. Qwen repeats the selection for every prompt, so the chosen columns and diagonals depend on the input. Qwen applies MInference using the original token positions. This selects the query key pairs to keep. It then uses DCA's distance labels when calculating the attention scores for those pairs. In Qwen's test on the 7 billion parameter model, this made Prefill roughly 4 times faster. But it reduces attention computation, not the temporary activations created by the MLP layers. At 1 million tokens, the temporary activations from a single MLP layer can require 71 gigabytes. Reducing that memory is the next problem. Those 71 gigabytes are temporary activations, but processing all 1 million token states together means keeping all those activations in memory at the same time. Qwen instead divides the input into chunks of 32,768 tokens. It processes the first chunk and stores that chunk's key and value vectors in the KV cache. It then discards the temporary MLP activations used to process that chunk. Qwen repeats the same steps for the next chunk. Only one chunk's temporary activations need to be in memory at a time. This is called chunked prefill. In the report's example, this reduces activation memory by 96.7%. That percentage does not apply to the KV cache. The cache continues to grow as each chunk is processed because later tokens may attend to tokens in every earlier chunk. Now put the 3 operations together. DCA remaps position distances. MInference selects which attention scores to calculate. Chunked prefill processes 32,768 input tokens at a time. Optimized GPU kernels and scheduling execute these operations efficiently. With full attention, the author's 14 billion parameter model took 12.2 minutes to prefill a 1 million token prompt on their H20 setup. With the complete optimized system, it took 109 seconds. That is about 6.7 times faster. Prefill is the processing that happens before the first output token. These numbers do not describe the generation that follows. Once prefill ends, Qwen can begin generating our passkey. Recovering it demonstrates retrieval across 1 million tokens. It does not yet demonstrate understanding across 1 million tokens. That distinction becomes clearer if we ask 3 separate questions. First, can the runtime accept a million token input? Yes, Qwen's stated limit is 1,010,000 input tokens. Second, can the model retrieve one fact from that input? In the author's passkey test, the 14B and Turbo models retrieved every tested key, including at 1 million tokens. Third, can the model combine information spread across the full input to answer a question that requires several steps? The report does not test that at 1 million tokens. The report's more demanding evaluations use shorter inputs. Longbench Chat tests up to 100k tokens, Ruler tests up to 128k, and LV-eval tests up to 256k. None of them evaluates more demanding tasks at the full 1 million. Those shorter evaluations still show why long context training matters. On Ruler at 128k, the ordinary Qwen2.5-1M's instruct checkpoint with DCA and yarn scores 78. Qwen2.5-1M's instruct 1M scores 92.2. Both use DCA and yarn. The second checkpoint also received long context training. So the evidence supports 2 strong claims at 1 million tokens. The runtime accepts the input, and the model retrieves a passkey from it. The report also presents results from more demanding evaluations at lengths up to 256k. It does not establish reliable multi-step reasoning across all 1 million tokens. Reaching the demonstrated result requires the complete system. Long context training, DCA and yarn for position handling, MInference for reducing attention calculations, chunked prefill for reducing activation memory, and the optimized runtime that executes them. Now we can answer the question from the beginning. Qwen never trained on a 1 million token sequence. Its longest training sequences contained 262,144 tokens. That training taught the model to use distant information. At inference, DCA remaps relative distances, and Yarn rescales the attention scores. MInference skips most attention score calculations. Chumped prefill processes 32,768 input tokens at a time, so only one chunk's temporary activations are stored at once. The optimized runtime executes these operations across multiple GPUs. Together, these methods let Qwen accept up to 1 million input tokens and retrieve a passkey across that length. The more demanding evaluations stop at 256K, so the report demonstrates million token retrieval, not multi-step reasoning across the full million tokens. That is what 1M means in Qwen2.5-1M.